Okay, you guys, welcome to Unit 5. We are done learning about the periodic table, but now we are actually going to use our knowledge of what we've learned depending on whether you're a metal or a non-metal and what that means in terms of either gaining electrons or losing electrons and seeing how that relates or affects chemical bonding. So there are actually 3 types of chemical bonds that we will be learning this year. Unit 5 will talk about the first 2 types. We're going to learn about metallic bonding and ionic bonding. And then actually we're going to spend an entire unit on the last type, which is covalent bonding. So we're in a big part of our chemistry class right now, and I'm so excited to talk about this. For our lesson today, you're going to need your notes handout on Intro to Chemical Bonding. You're also going to need a blank periodic table. Yes, we are coloring things again. And then you're also going to need this cute little foldable thing that I've given you and we folded together because we're actually going to be coloring this because this is going to be a particularly challenging concept, and we're going to be using this little foldable booklet over the next 2 units to help us do things like writing formulas and naming things here. Then lastly, I'd like for you guys to also get out your list of polyatomic ions. We're going to add a couple of things on there to hopefully make this whole concept of bonding a little bit easier. You'll also need 2 colored pencils today. You will be using the same colored pencils as I am. We're using red and blue colored pencils for our notes lesson today. Okay, so let's define, first of all, what is a chemical bond? So a chemical bond is any attractive force between atoms or ions that holds them together. So now we're going to get out our periodic table. We are ready. We are actually going to color our periodic table. And we're going to color them with the 2 colors that I've given you, the red and the blue. I have mine already colored for you guys. So as y'all are working through this, you can kind of look at what I've got. Let me see if I can lift this up and make this a little bit better to see. Yes. Okay. So I have my staircase here, and we know my staircase divides my metals and my non-metals. And some of you guys are like, well, what about the metalloids in there? Yes, the metalloids along the staircase, besides aluminum, he's a true metal, do show tendencies of having both metallic and non-metallic like properties. That is not going to really affect us with the bonding lessons that we'll be doing today. What is going to be important is that we know my metals, we think red. We see nonmetals, we think blue. And hydrogen over there, do not forget about him. He is also a nonmetal. He's just being really sneaky, really funny. So we're coloring this red and reminding ourselves that everything to the left of the staircase is a metal. And we're coloring my nonmetals blue and reminding me that everything to the right of the staircase is a nonmetal. I've also added a couple of new things on here. Well, first of all, the valence electrons and oxidation numbers are not new. We've put them on a lot of our periodic tables before, but they're still important now. So your valence electrons, keep in mind, group 1 are my alkali metals. They have 1 valence electron. Group 2, my alkaline earth metals, they have 2 valence electrons. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18, my noble gases, have 8 total valence electron, a stable octet. Now, depending on the number of valence electrons you have, we know that determines what charge the most common ion will make. Group 1 will lose his electron to make a +1 charge. Group 2 will lose the 2 electrons to make a +2. Group 3 is +3. Group 4 is +4. And then once I get to group 15 with 5 valence electrons, it's a -3 charge because he gains 3 to make that stable octet. Finishing off with a -2 charge, a -1 charge, and then my noble gases do not have an oxidation number because they are completely stable. Okay. After you have colored that and labeled your oxidation numbers and valence electrons, I want us to, a periodic trend, you guys. Here's electronegativity. I really, really want y'all to show the trend lines for electronegativity because electronegativity actually helps determine what type of bond my elements will make when they form bonds, which is really exciting. And then finally, the last thing, this probably won't make sense until next week, but I have written some numbers on some of my metals right here. Silver, I've written a +1. Zinc, I've written a +2. And then aluminum, I've written a +3. These are the oxidation numbers for these specific elements, okay? I think I alluded to last time that the transition metals, we don't write anything on top of their groups because their number of valence electrons and oxidation numbers can be a little bit wacky and a little bit different and not predictable. But what I've written here, silver will always have a +1 charge and zinc will always have a +2 charge. You're like, doesn't aluminum obviously have a +3 charge if he is in that group? I'm like, yes, but this is what helps me remember that silver is 1, zinc is 2, is because it makes a really cute little arrow, 1, 2, 3, and that's how I remember. Okay, now this will be important when we start writing chemical formulas for some of these bonding types that include those metals. And then, okay, I think we're ready to get going with kind of unpacking the basics of these different bond types. Okay. So we've colored our periodic table. Now we got to know, well, why? Why do atoms bond? Atoms bond in order to achieve a stable octet, which we've heard before, that we know that is 8 valence electrons. They do so by, oh, here we go, losing, gaining, or, oh, y'all, they can even share their valence electrons. So the result of this will actually lower the overall potential energy of the atom, which makes us stable. Let's zone in on that last sentence. Lowers the overall potential energy of the atom. That is a lot of super sciencey words. Basically what this is like is it's like if I am very anxious or I've got a lot of anxiety, I've got really high potential energy, and that is not a comfortable state for me to be in. I'm going to want to do my meditations and my prayers and my relaxing to calm myself down, and that is where I am happy and stable. So when I think about lowering the potential energy of the atom, I think about lowering the atom's anxiety. That would make it more stable. That would make me feel more stable, at least. Now this kind of brings us into why our noble gases do not bond. You guys, they have that stable octet, so they are not going to lose, gain, or share electrons with other atoms to make chemical bonds. Down here is a cute little picture. This is actually a covalent bond type. We'll learn about it here in a second, that covalent bonds are bonds that share their electrons. So here I have 4 chlorines, and it looks like they're stuck together to a carbon, and all those circles, if I count all of the dots around every single one of those atoms, I can notice that everybody has 8. Now, they did not start off with 8 valence electrons specifically. We know that chlorine's in group 7 with the halogens. He has 7 to begin with. Carbon's in group 14, he's got 4. But when they join together and overlap their electron clouds, they can share their electrons to make them feel like they each have 8. That was a long tangent on covalent bonding, and we're not even doing covalent bonding fully until next unit, but I just got real excited because that's super fun. Okay. So on your notes page, you have a lot of pictures in between these terms, but I wanted us to write those terms down fast and what it means in terms of what the electrons do. And then we're going to look at the pictures and talk about all the good things. Okay, our first of our 3 bond types is a metallic bond. And if you can see, I wrote metals in parentheses. Maybe this is why she had us color our periodic table again. Yes. So in metallic bonding, electrons are delocalized. That's a weird word. We'll learn all about that word here in a second. So there is an electrostatic attraction between cations and the delocalized electrons. Zipping on down to ionic bonds. Ionic bond is between a metal from this side of the periodic table and a nonmetal. In ionic bonds, electrons are transferred. And then you will have an electrostatic attraction between the cations and the anions. And then finally, lastly, our third type of bond is a covalent bond, and that's between nonmetals. Oh, this side of the staircase. And in covalent bonding, the electrons are shared. And the covalent bond itself is an electrostatic attraction of both of the atom's nuclei, which is positive, on their shared electrons. Okay, so we're going to get out our colors again. And we're going to actually color these things on our notes page. So I'm going to get mine out too. And we've got our notes page. And you have already filled in that metallic bonding is electrons are delocalized. Ionic is electrons are transferred. And covalent is electrons are shared. Our periodic table, we colored blue for nonmetals, red for metals. So I would like for you to actually color the term metallic bond red. And I want you to color the, in parentheses, metals. Ionic bonding is made between a metal and a non-metal. So I would like for you to color half of the ionic bond red and the other half blue. And Sabatka, does it matter which color I do first? Yes, please do your metal red first and your non-metal blue second. And then I can color the words metal and non-metal. And then finally we have covalent bonding, which is between nonmetals. So nonmetals are blue, so I'm going to color it blue. Okay. So as you can tell, this is a nice visual that lets me know, oh, this is why those three types of bonds are different. And you should be able to determine what type of bond you have, not by looking at a picture. First, you can tell what type of bond you have by figuring out what kinds of elements are in there. Now, I want y'all to get out your little foldable booklet. This foldable booklet is called a nomenclature booklet. Nomenclature is a fancy term to mean naming or writing formulas for compounds and chemistry. So if you'll notice, my booklet is divided in half. This side right here is all about ionic naming compounds and ionic writing formulas. As you can see, I have done my coloring here. We know an ionic bond is between a metal and a nonmetal, so I have colored half of this title red. If you'll notice, I have a big M there. I think that means metal. I think that means nonmetal. And if you'll notice, I put a positive charge and negative charge. I'm getting ahead of myself, but a lot of this is going to make sense here in a second. I just wanted to get our kind of coloring done today. Okay, we are not worrying about what is inside of those flaps. You are already overwhelmed because, oh my goodness, that is a lot of words. And I agree. This is why the naming and nomenclature piece of our course takes a long time, because we're going to really have to work hard to make sure it's good. Okay, and over here we got my covalent stuff. We know my covalent stuff is between non-metal, so I'm coloring all of that blue. And if you'll notice, I put little non-metal. And oh my gosh, there's a line between it. I wonder what that means. Ooh, I'm excited to find out. So this is meaning that there are different rules for how I name and write formulas for ionic and covalent compounds. Yes, there are different rules. I am sorry to tell you. You were probably also asking yourself, like, where is the metallic bonding? Metallic bonds don't have tricky naming situations, and for that you are grateful, trust me. I do want to add a little bit more on this ionic stuff. We know that ionic bonding, I've told you, is between a metal and a non-metal. Well, I gave it a positive charge because we learned last unit that, oh yeah, my metals have these positive oxidation numbers. They lose electrons, so they make positive cations, right? And then my nonmetals on the other side of the periodic table, they've got the negative oxidation numbers, which means they gain electrons to become anions, right? So I got some news for you. It is between a metal and a non-metal, but sometimes our metals are not just one of these guys from the periodic table. And sometimes our non-metals are not one of these guys from the periodic table. I could also be a polyatomic ion. So on y'all's polyatomic ion list, you're like, oh my gosh, this is so nutso. Y'all, I have a bunch of polyatomic ions that have -1 charge, -2 charge, and a -3 charge. Those have negative charges. So if you want, in fact, you will, go ahead and put a little indicator between all three of these categories and write non-metal in parentheses. And you were like, oh my gosh, where is she going with this? To give you a preview, what I'm telling you is that all of these atoms within a polyatomic ion are collectively going to act like a non-metal in its entirety, okay? So yes, I have my nonmetals from the periodic table, but we will also be using these polyatomic ions filling in as a nonmetal because they make these negative charges. Okay, we also have a real awkward guy down here, ammonium. Y'all, he's my only positively charged polyatomic ion, but he's got a positive charge, so you guys, he can make ionic bonds, and he will be acting as a metal, okay? So we have now indicated on our polyatomic ion list that my nonmetals polyatomic ions are these negative ones, and my metal polyatomic ion is this one lone ammonium. Going back to your foldable, I'm a lot of upfront at you guys today, but we got a long time to really dive into all this stuff, so don't you be overwhelmed. Just flip back to the back of this thing, I gave you a chart of your polyatomic ions back here, which you were so excited. I'm going to zoom in a little bit. Now, I've colored my non-metal negative polyatomic ions blue, right? Do not color too darkly because you'll want to be able to read this list. And I've also colored my ammonium positively charged metal-like polyatomic ion red because he's acting like a metal. So when I need to use these polyatomic ions to write formulas or name things, that reminds me what place they're supposed to be in. The other color thing that I did right here is this says transition metal cation oxidation numbers. Remember on our periodic table when we colored it and I mentioned to you guys that silver always has a +1 charge and zinc has a +2? I thought it might be a good idea to remind us that, hey, well, you know what? That's going to be a metal representative whenever I need to use silver or zinc. I've also told you what the charge is on those transition metals. Always. Okay, so we just did a lot of coloring. Let's go back to the lesson. That was real intense. Yay. But those will be your tools, your colored periodic table and your colored foldable booklet and your list of polyatomic ions, and you'll be ready to go. My chemists, I'm excited about that. Okay, so we already colored our book. Yay for us. Now I kind of want to unpack these 3 types of bonds a little bit more. So my metallic bond is made up of metals, the red guys, the guys to the left of my staircase. And what makes a metallic bond is that these metals electrons are delocalized. We will have an entire lesson on metallic bonding, so I'm going to try not to get too excited about it here. But what I'm looking at when I say delocalized is I have all of my metal atoms, and you guys, they all look positive now. Well, that's because all of these metal atoms in a metallic bond lose all of their valence electrons to this area around them. And if they're losing their valence electrons, we know losing electrons makes you positive. So the metals turn into cations when they make a metallic bond. What it is called, it's called the sea of electrons. I like to think about it as like a bunch of kids at like Chuck E. Cheese swimming through one of those ball pits. Okay, where the kids are the metal cations and the balls are the valence electrons that have been delocalized from all of the atoms there. So you're like, that does not look like a bond to me. I thought bonds were where, like, you know, we draw little, you know, structures with the lines in between. I was like, yeah, you guys, 2 out of our 3 types of bonds are not like physically connected together. So you're like, well, what is going on to make this stuff stick together? Y'all, I see some positive things and I see some negative things here. Oh my gosh. We know positive and negative attract. So any sort of attraction between a positive thing and a negative thing is what's called as an electrostatic attraction. And some of you guys are like, oh my gosh, on my notes page, it looked like every single one of my bond types had some sort of electrostatic attraction. Yes, that's the essence of any type of bond is an electrostatic attraction. Now, depending on the bond type, that electrostatic attraction is going to be maybe from differently charged positive and negative things. Specifically here in a metallic bond, my positive thing is that positive metal cation, and that negative thing is those delocalized electrons which are swimming freely throughout the metallic bond structure. So that is very exciting for us. We love metallic bonds. Okay, moving on to ionic bonds. Ionic bonds have one of each, metal and nonmetal. In an ionic bond, the electrons are transferred. You guys, we had a preview into this last unit. I'm super getting excited. We talked about metals. They lose their electrons in order to become happy. Non-metals, they gain their electrons in order to become happy. Here it is in action, okay? My metals will lose an electron, not just to the abyss, unless you're in a metallic bond, but they will lose their electrons to a non-metal who will gain it. Now everybody becomes happy. So guys, this is an ionic bond formed between sodium chloride, sodium and chlorine. We know sodium group 1 has 1 valence electron. He pops it off. Chlorine had 7. And now you guys, everybody is so super happy. You're like, that is amazing. I'm now also looking at 2 things that are not connected together. Yeah, ionic bonds are not physically connected. But what I've created is a positive ion and a negative ion. That looks like an electrostatic attraction to me. And yes, so ionic bonds are just an electrostatic attraction between a positive cation and a negative anion due to the transfer of those electrons. So y'all, we drew these little dot structures last unit. Here it is. This is your ionic bond. Oh my gosh, I love that so much. And this is a structure of an ionic bond. We call this structure a crystal lattice because it is an alternating structure of the cations and anions all spread apart surrounding each other to where no two like charges are in contact with each other. Okay, so very cool. That is our ionic bond. Our last type of bond, you guys, here is you're connecting the dots, holding hands. This is my type of bond between nonmetals where electrons are shared, okay? So y'all have done some Lewis dot structures before in the past. We will be doing this in Unit 6. But that line in between the atoms shows me that the electrons are shared in a covalent bond, okay? Here's a little bit better of a visual image showing that shared pair of electrons. One of the electrons from the pair came from oxygen. The other one came from the hydrogen. As a result, they are now satisfied and happy. I'm trying not to get too into this. We have lots of time to unpack this. But yes, we have overlapping electron clouds. So these covalent bonds are physically connected. Electrostatic attraction here too. You're like, oh, I don't see positive and negative things. Well, the electrostatic attraction in a covalent bond is the most confusing one for me. But it's the electrostatic attraction between the positive nuclei of each one of the atoms and that shared pair of electrons. So both of these nuclei are going to be pulling equally on that shared pair of electrons. So that's the electrostatic attraction in a covalent bond. Okay, so recapping, metallic are made from metals where electrons are delocalized in the sea of electrons. Ionic are made from a metal and a nonmetal where electrons are transferred from the metal to the nonmetal to create that cation and that anion in this wonderful crystal lattice structure. And then finally, my covalents are from my nonmetals where they hold hands and share their electrons. Super exciting. The key thing here is even though all the bond types are different, is y'all, the electron is involved in making the bonds. And the purpose of all of these bonds is for each one of the atoms involved in the bonding to achieve a stable octet. Yes, metallic, they lose their valence electrons because, oh, now underneath, they got a stable octet underneath. Ionic, transfer, oh, now the metal has a stable octet underneath. Oh, and the nonmetal, that gained one, is stable. And then in covalent, they share to where they each satisfy their octet through the sharing of electrons, which is really, really, really exciting. Okay, so now we have a super fun video that kind of unpack or summarize these three types of bonds, and I thought this would be a great kind of intro to what we're about to dive into for the next, I want to say, month and a half on all these bonds.
This video explains how the three types of chemical bonding work. First, ionic bonding, between metal and non-metal atoms, for example, sodium and chlorine. All metal atoms generally have between 1 and 3 electrons in their outer shell. For example, sodium has 1 in its outer shell, shown as a cross. Non-metal atoms generally have between 4 and 8 electrons in their outer shell. Chlorine, for example, has 7, shown as dots. But all atoms want a full outer shell, so the metal and non-metal atoms do a deal. The metal sodium atom gives its electron away, and the non-metal chlorine atom receives it. Now, they both have full outer shells. But where does the ionic bond come from? Both atoms were neutral, but after trading the electron, the sodium is now a positive ion, and the chlorine is now a negative ion. The oppositely charged ions attract, causing the ionic bond. Many ions attract to form a giant lattice structure. Ionic compounds have interesting properties. Because ionic bonds are strong and act in all directions in the lattice, it takes a lot of energy to break the ionic bonds, giving ionic compounds high melting points. Second, covalent bonding, between non-metal atoms. Let's look at water. Again, all atoms want a full outer shell. Oxygen has 6 outer shell electrons, but needs 8. Hydrogen has 1 electron in its outer shell, but needs 2. But rather than swap electrons like ionic bonding, covalent compounds share electrons. The oxygen atom shares 1 pair of electrons with each hydrogen atom. Each hydrogen now has 2 electrons, and the oxygen has 8. All of them are happy. So where does the bond come from? The shared pairs of electrons are negative, and the nuclei of all atoms are positive. The attraction between them is the covalent bond, and like ionic bonds, they are very strong. Water is one of 3 kinds of covalent compound, called a simple covalent compound. Although covalent bonds are strong, the forces between the small molecules are weak, so it takes little energy to break these weak intermolecular forces, meaning that water and other simple covalent compounds have very low boiling points. However, giant covalent compounds like diamond have very high melting points due to the covalent bonds. And finally, we have metallic bonding between metal atoms such as iron. Iron has 2 electrons on its outer shell, but metal atoms work as a group and share their electrons between them. The electrons form a sea of delocalized electrons, which are free to roam throughout the giant lattice. Where does the bonding come from? Well, the positive nuclei are all held together by the sea of delocalized electrons, like a strong glue. The bonding is very strong, meaning that metal generally has very high melting points. So these are the 3 types of bonding. For a closer look at covalent compounds with some examples, see the following video. And don't forget to like and subscribe.
Okay, so I love that video because it's simple, it's easy to understand, and I think it does a great job of recapping the basic information of these 3 bond types that we just talked about. Last thing I want us to do is I want to talk about the relative strengths of the 3 bond types. You heard in that video that the guy was like, oh, they're all strong, they're all strong, they're all strong. Yeah, but if I were to rank each one of the types of bonds in terms of their relative strength to each other, you guys, and this may surprise some of y'all, metallic bonding is usually my weakest type of bond out of the 3. Next up higher is my ionic bonding, and then my covalent bonding. And some of y'all were paying attention to the video and being like, well, I thought he said like it was like really weak and stuff. And we will unpack all of that when we get to the covalent bonding next unit, but there's a little bit more to it. But yes, the actual covalent bond is the strongest of my 3 types of bonds. Okay, so now I'm ready to really get into each one of these 3 types of bonds.